So this talk will be on the new features in ASTRA-sim that we've been adding over the past few months. And it will be presented by myself, Vinay, Bilwan, and Ruchi Shah from AMD Research and Advanced Development. Yeah, there we go. Yeah, so this talk will be divided into 3 sections. So in the first section, I will be talking about the support for JSON chakra traces. And in the second part, Wilwan will take over and talk about the support for custom collective plans in ASTRA-sim. And in the last part, Ruchi will talk about the logging and visualization features that we have been adding to ASTRA-sim. If you have attended the earlier parts of this talk, then you're familiar with how the input workload is represented in the form of chakra execution traces, which is in the protobuf format. So in this format, we have one chakra ET representing the workload graph per NPU. And the ET feeder in chakra will consume these input workload graphs and then builds the dependency graph in memory, which will be presented to the ASTRA-sim workload layer. If you're familiar with the protobuf format, then you know that it is in the form of marshaled binaries. So the advantage of using something like a marshaled binary is that it is compact and fast. However, it is not human readable. So that is one of the major hurdles that we were facing when doing development in ASTRA-sim. That is, if you want to generate a chakra trace so in the protobuf format, then as previously demonstrated, you have to use the Python script, the chakra generator or a chakra converter to write your chakra ETs into this format. And also, if you want to inspect the trace itself, then you'll have to convert the trace into a different format, which is human readable, and read in the file and inspect what is going on within the chakra trace. So in order to alleviate some of these disadvantages, we added in support for JSON format. So like previous formats like protobuf, you can either have one JSON ET per NPU or have a single JSON ET that represents the entire workload. And the ET feeder will consume this JSON ET and then construct the dependency graph in memory, which in turn can be presented to the ASTRA-sim workload layer for processing. So here's an example ET. So in addition to the workload graph, you can have global metadata such as workload name, the number of NPUs over which you're executing this workload, the SOC on which you're executing this workload, etc. And we also have support for indicating communicator groups or COM group IDs as shown here in the global metadata itself. So in this case, by having a global list of communicator groups, your workload graph can reference to the COM group IDs instead of repeating it every time within the workload graph nodes itself. So in order to maintain backward compatibility, that is, we want to support both protobuf as well as the JSON chakra format, we have sort of replicated the ET feeder functionality for the JSON format as well. So previously, when we had the chakra protobuf trace, the nodes in the input workload graph would be read into a data structure called ET feeder node, and it was presented in the previous talks as well. And the ET feeder, which is a tool, would go through the different ET feeder nodes and build the dependency graph, which would be presented to the ASTRA-sim workload layer. So now with the JSON format, we have an analogous data structure called JSON node. I know, very creative name, but it essentially acts as an analogous data structure to the ET feeder node. And we also have something called the wrapper node that includes the functionality of the ET feeder for the JSON format. And not only that, it presents a common API that can be used in ASTRA-sim workload layer, so that depending on the file format, we have support for both the protobuf as well as the JSON chakra trace. So here I have a short demo of how you can use both the protobuf and the JSON chakra traces. So let me play this video clip here really quick. So as you can see here, I am running ASTRA-sim. Here's a script that runs ASTRA-sim, and I'm providing protobuf in chakra execution trace as input. So in this case, this consists of 2 communication nodes and 1 compute node. And I am running it in ASTRA-sim using Omnet++ as backend. So that is something that we use internally at AMD. So that's what I'm using. And as you can see, because this is a sample input, it ran pretty quickly to completion. Now here's the same workload represented in the form of, let me skip the video here. Yeah, there we go. Here's the same workload represented in the form of JSON. So as you can see, this consists of 2 communication nodes, that is 2 all-to-all nodes and 1 compute node. And I will run this in ASTRA-sim. So let me change the script here. So the file names are the same. So I'm just changing the file extension from ET to JSON to indicate a different input file. And I run ASTRA-sim with this input file, and you can see it completed pretty quickly as well. So now inspecting the logs here of ASTRA-sim for the 2 inputs that we had. So the first one is for the JSON input format. You can see the logs and how ASTRA-sim completed. Keep slipping. So let me go back to part of the video here. Yeah. So yeah, this is the logs for the JSON file. And you can see the logs are identical because all we did was we changed only the input file format. So we did not change how the dependency graph gets built into memory. So what ASTRA-sim sees is essentially the same input, and you can provide either the protobuf format or the JSON format. So with that, I will hand it over to Wilwan to talk about custom collective plans in ASTRA-sim.
So what Vinay had just presented is about upgrading the workload layer and how to represent the chakra execution trace. So the protobuf-based chakra execution trace was not human readable. So we put a lot of effort to migrate to the JSON by keeping all the features of the chakra, the protobuf-based chakra, so to make it human readable and to make it easier to write more chakra execution trace and so on. So meanwhile, my change that I'm going to present here is more of a system layer change, where instead of simulating the textbook collective algorithm like ring or direct, I explained before the coffee break, we are bringing the simulation capability of running custom, very complex collective algorithms inside ASTRA-sim. So first, why we need such custom collective plans? It's because the dynamics and the nature of the network and the system of the distributed ML system is becoming really complex. So even for the textbook-based collective communication algorithms, the latency optimal and the bandwidth optimal collective algorithm is different. So for example, this ring algorithm is taking log is O of n steps. So it's more of a bandwidth optimal, whereas the recursive halving doubling algorithm shown here, the number of steps you take is of log n, but your message size, the message size you're transferring is way higher. So it only makes sense to run when your collective size is quite small. So again, just to run your single collective, the latency optimal and the bandwidth optimal collective algorithm is different. Plus also the underlying network topology you're running is also quite distinct. So here, just as an example, just put the Dragonfly. Dragonfly is neither ring or suitable for the recursive halving doubling. Plus, over the Dragonfly, the latency optimal and the bandwidth optimal collective algorithm would certainly differ. So that's why we need this is why we need to design, represent, simulate, and run custom collective plans, which is tailored for your collective size, as well as the underlying network topology you're running. So with that, there has been some pushes in terms of representing the custom collective plans and designing them. So one effort is called MSYCL-lang, which is represented in last year's AS+, where you design a domain-specific language in Python to describe the custom collective plans. So this is an example of the MSYCL-lang DSL. Here, this is a simple ring algorithm represented in the DSL. Basically, you can define a chunk and decide where you want to send the chunk and use this command called copy to send the chunk. You can basically think of, because your looping a for loop in a very systematic way. This is only representing the ring altogether, but you can think of, you can use this API to really capture very complex custom collective plans. And this is another thread, not the DSL. As I mentioned, the another thread of this is to create a collective communication algorithm synthesizer, where the input to the synthesizer is the target network topology, as well as the collective configuration, like the collective size. And the synthesizer will optimize and come up with the really well-suited optimized custom collective plan, which can be quite complex than the ring or direct or Helling doubling. So there has been multiple efforts in terms of designing the synthesizer. My latest endeavor was called Tacos, which I will present 2 days later, as I mentioned, and advertise. But there has been other work such as TechCol, ForestCol, and so much more. So there are synthesizers generating this custom collective plans, as well as the DSL, design-specific, domain-specific language, to represent arbitrary custom collectives. Then, once this work has been done, how we should standardize and represent the custom collective plan. So there has been 2 proposals. One is for the two-sided communications. We are using this XML format, which is defined in the MSYCL paper, which we call a MSYCL IR. So for the two-sided communications, we can represent custom collective plans in XML file. Whereas the work in progress is for the one-sided communication, is called MSYCL++, which we can capture and represent the custom collective plan in JSON file. So for today's talk, I will concentrate on this two-sided communications, how we represent that in XML, and how we support that in ASTRA-sim. So as I mentioned, we have several different threads to generate the custom collective. For example, the MSYCL DSL, as well as the synthesizer. And when we lower or synthesize, it will generate the standardized custom representation called XM custom plan representation in this XML MSYCL IR format. So this is how the actual MSYCL IR format looks like. So this is an example of the MSYCL IR, where you really encapsulate all the communications happening between all the GPUs, the thread blocks, or the work groups. So for example, here in this case, you can define GPU 0 and its thread block or work group 0 is sending a message to GPU 1, as well as after you're done this, you're receiving a message from GPU 1 back to the GPU 0. And you can see it's basically representing line by line the order of send and receive in this in this XML representation. So as I mentioned, what's happening in ASTRA-sim is that it parses the Chakra ET in the workload layer. And whenever we have to run the collective communications, as I showed how the system layer is working, it will break down the collective into multiple send and receive and send it to the network simulation backend so that the network can simulate that. But the objective in our new work is to update this ASTRA-sim flow to enable the simulation of this custom collective plans represented in the XML. So what we've come up with is to update the ASTRA-sim so that we can pass the XML as well as the workload input file. And the ASTRA-sim system layer will parse this custom XML plan and represent it in the internal Chakra ET representation. We will completely bypass this textbook-based basic collective plans. And this parsed Chakra ET, consisting of multiple send and receive operation, will directly talk to the network simulation backend. So this is how we're supporting the custom XML plan, bypassing the originally existing baseline collective algorithms in ASTRA-sim, and be able to simulate the custom collective representations in ASTRA-sim. So yeah, this is the parsing result as an example. So when we pass the XML file into the ASTRA-sim, it will parse that XML file entirely and come up with the actual plan and dependencies, when to send which chunk from where to where. So you can see ASTRA-sim will parse the XML, keep this file internally, and when we actually start running the actual simulation, and when you phase to run the collective communication, it will bypass the FSM I showed. Instead, it will follow the patterns and send and receive operations shown here. So yeah, this is the end-to-end, the summary of how ASTRA-sim is simulating the custom collective. So when we generate the XML representation, which will have a bunch of send and receive operations, it will internally parse this and come up with this complex send and receive tree. It will completely bypass the FSM in the system layer. So when you run the simulation and whenever you want to run the collective communications, it will instead start running this. And once done, pass the pointer back to the workload so that you can run the end-to-end simulation. So this is a very simple demo of running the custom collective. And as you can see, we just pass the XML file. It will bypass the existing text-based, the textbook representations, the collective algorithms, and give you the custom collective simulation results. So with that, yeah, I'll finish my part and pass my pointer to Ruchi to explain about the logging and the visualization efforts in ASTRA-sim.
Thanks, bro. So, right, this is like the third tracer that we're looking at today. So, okay, just to give you a motivation, why we created this visualizer. So right now, everything is work in progress. For textbook implementations, the thing is that you can still intuitively identify the data transfer patterns. But for synthesized plan, which eventually get more complex, all you have is a bunch of send and receives, and you have to identify the data dependency, the transfer patterns, all of that. So having a visualizer kind of became really handy while we were working on, while we were building that infrastructure in ASTRA-sim. So at the moment, all we're using this visualizer is to optimize the code. So identifying if the patterns are working as expected. So we're like comparing with the XML files, the XML plans that Bill mentioned, and then making sure that the patterns, we see those dependency patterns executing as is. So right now, it's what you see on your left-hand side is the chakra graph that we generated. So like Will mentioned, these XML plans get consumed by by chakra, and it will create the chakra graph. And then the chakra graph will then be consumed by ASTRA-sim to generate these sends and receives communication and compute nodes. So what you see on your left-hand side is the chakra graph, and you can see that there is communication. The blue ones are the communication nodes. The green ones are the comp nodes. Now, what you see on your right-hand side is the actual visualizer. Right now, the granularity that we're showing is the GPU level and the workgroup level, because we're still building. I mean, eventually, we'll still build this visualizer to show more finer granularity of packet sizes. But right now, it's just workgroup and GPU level. Just to give you like a sense of why this visualization is effective is because right now, if you see on your left-hand side, there are comp send nodes. And if you look at the computation node, it looks like everything is being sent in parallel. But when we actually visualize it and how ASTRA-sim consumes it and sends it, we were able to identify that the communication node does happen in parallel. But when we send the computation home, it's actually staggered. It's happening one after the other. So that was a really good insight that the visualization was able to give us. And eventually, when we have more complex topologies that we're going to execute, definitely the visualizer will be very helpful. At the moment, with respect to the visualizer, we have like two features. One is that we can toggle between the different access events. We can log different events at different times, and we can only enable and disable specific events that we want to log. The second thing is, if we're running a really large simulation, and if you want to log only like a specific timeline, you can actually run a script with the start and the end timeline, and you can only visualize a part of the entire logged script. So you don't have to really see everything. So if you're trying to isolate a specific issue, then the visualizer will be very handy. And yeah, this is a 4 GPU setup. So that's pretty much from the visualizer side. If you have any questions, I have to answer. But that's completely work in progress at the moment.